First, let's remind ourselves of auxiliary qubits in quantum computation. These qubits serve as temporary storage. For example, here is a V-chain implementation of a 4-controlled RY gate with an auxiliary qubit. Under the requirements that the auxiliary qubit is at the 0 state, it stores the AND operation on the first 4 control qubits, Q0 to Q3, and the operation result is then passed to toggle the RY gate. Afterwards, the auxiliary qubit is uncomputed to be reused in other computations. Some functions, like multi-controlled operations with many control qubits, can have different implementations, which differ by the number of auxiliary qubits used. The Classiq built-in function library has a multitude of such functions. A trade-off exists between the number of auxiliary qubits used to construct the gate versus its depth and CX gate count. Let's synthesize a circuit with a single MCX gate of 10 control qubits. The total number of functional qubits is 11. In addition, let's optimize the CX gate count. The CX gate count, or another Clifford 2-qubit gate, such as CZ, is a good proxy for computation time and algorithm success rate in the NISQ era, and it is independent of the individual single qubit gates used to form a universal gate set. Here, we use CX and U as basis gates. First, we synthesize without any width limitation. We now observe that the resulting circuit uses 20 qubits, the 11 functional ones, and 9 auxiliaries. As expected, the synthesis engine chooses an implementation that uses more auxiliary qubits to reduce the CX gate count. Now, let's limit the width to 11 qubits. As a result, the synthesis engine chooses an auxiliary-less implementation. As expected, the CX gate count is higher due to the additional hardware restrictions. Let's discuss a more advanced example of hardware-aware synthesis that considers the limited qubit connectivity in superconducting architectures. Before that, let's take a step back and consider the physical limitations imposed on classical computation. In a world without memory limitations, every classical computation done once could be stored forever in memory and queried upon request. A technique commonly referred to as dynamic programming utilizes that to reduce computational complexity. We store the intermediate calculation results to avoid repeating them multiple times. But for large enough cases, this ideal picture breaks down. The place on the on-chip memory, or cache, runs out, and the operating system instead routes new intermediate results to the random access memory, or RAM. Practically, the communication between the CPU and the RAM is orders of magnitude slower than the communication between the CPU and the cache. So we expect the storage operations to exhibit a diminishing return behavior at some point. Then we prefer to repeat calculations instead of storing them due to communication overheads, a choice some might find counterintuitive. Back to the quantum world. The computational architectures are still premature compared to their classical counterparts. Particularly, quantum memory models in the NISQ era are like that. Surprisingly, we can still find examples of the quantum analog of such behavior. First, let's ask Classiq's synthesis engine to construct a 50 control qubit MCX gate and optimize the circuit on the CX gate count. We assume a fully connected qubit diagram, so there are no restrictions on the entangling gates. The resulting circuit requires 100 qubits, 51 functional ones, split into 50 control qubits and a single target qubit, and an additional 49 auxiliary qubits. This implementation uses many auxiliary qubits to reduce the CX gate count as much as possible, just like we saw previously. Now let's ask the synthesis engine to generate the same MCX gate, but now for the IBM 127 qubit Eagle processor, a superconducting architecture with limited connectivity between the qubits as shown in this image. The connectivity diagram is formed by vertically stacking lines of 14 or 15 qubits and connecting them via alternating 4-qubit layers. We select the quantum device and synthesize the circuit. It takes a bit longer due to the qubit routing involved in the circuit compilation process. The resulting circuit now uses 75 qubits only. Let's explain this result. As explained in the previous lesson, forming an entangling gate like CX between indirectly connected qubits requires routing the qubit state using swap gates. And each swap gate costs us 3 CX gates. Gate-level compilers perform optimization passes to reduce this number of necessary swap gates. However, this example shows that a turning point still exists, resembling the classical case. Using too many auxiliaries results in routing overhead bigger than the gain obtained from temporarily storing the quantum computations. Note that this result doesn't mean that the best possible implementation of MCX for this specific hardware consists of 75 qubits. It tells us that this is the best possible implementation among the functions available in Classiq's library. Still, this highlights the diminishing return behavior of adding too many auxiliaries. I hope you enjoyed this lecture. We got much deeper into the heart of what the Classiq engine does and how it can be used when synthesizing with specific hardware needs in mind. See you in the next lecture.